Hello all. Here we are going to discuss about the angle and orthogonality in inner product spaces. So first let us see what is Cauchy's inequality. Let U and V are elements in inner product space capital V. Then the Cauchy-Squart's inequality is defined as modulus of inner product U comma V less than or equal to norm U into norm V. And this is what we already come across for the Euclidean inner product. So these are all the properties of length and distance which we have come across in module 2 already. The distance and length will always be greater than or equal to 0, and it is equal to 0 if and only if u is equal to 0. For this case u is equal to v, and k times norm ku is equal to mod k norm u, and the last one is nothing but the triangle inequality. Similarly for properties of distance. So next is the concept of calculating the angle between any two vectors u and v. So let u and v be two vectors in capital V, that is the inner product space. Then the angle between u and v is defined as cos theta is equal to inner product modulus of inner product u comma v divided by norm u norm v, where theta value lies between 0 to pi. And we can tell that when the inner product is 0, so we can conclude that u and v are orthogonal to each other. And if they are orthogonal to each other, there comes the concept of Pythagoras theorem, that is norm u plus v square is equal to norm u square plus norm v square. So next is the concept of orthogonal complement. Here W is a subspace of capital V, and when you consider one vector u and v, if that vector is orthogonal to all the vectors in W, then we can tell that u is orthogonal to W itself. Okay, and the set of all vectors in V which are orthogonal to W is nothing but what we call as an orthogonal complement of W, and we denote that orthogonal complement as W perp. So obviously with this what we can conclude is W perp will be a subspace of V, and also the only common vector between W and W perp, as those two are orthogonal to each other, the only common vector will obviously be 0, and W perp the whole perp is equal to W. So next is a concept. Here if A is an m by n matrix, then the null space of A and the row space of A transpose are orthogonal complements of each other. Similarly, null space of A transpose and column space of A will be orthogonal complements of each other. So here we need to determine whether the following pair of vectors are orthogonal to each other or not. So to check whether they are orthogonal to each other, we need to use this concept, that is we need to check u dot v is equal to 0 or not. Okay, so for the first one we are having vectors as -1 3 2 and v as 4 2 -1. When you take dot product, because this all these are vectors, and for the case of vectors the Euclidean inner product and the inner product are the same. So that is we need to take dot product between these two vectors. So -1 into 4 is -4, 3 into 2 is 6, 2 into -1 is -2, so you are getting 0. Therefore we can tell that u and v are orthogonal to each other. And for the case of B, we are getting that -6, so not equal to 0, so therefore they are not orthogonal to each other. So for the next sum, they gave that the value for u is 1 1 -1 and v is 6 7 -15, and norm ku plus v is equal to 13. We need to find the value for k. Okay. So k times u is nothing but k is a scalar multiple. So k times u will be k comma k comma k. And ku plus v is nothing but k plus 6, k plus 7, k minus 15. Sorry, it is minus k minus 15. So when you take norm for this guy, it is nothing but the square of each individual elements, and what we will be getting here is the root symbol. So to remove that root, I need to take squaring. I need to square on both the sides. So these two will get cancelled. 13 square is nothing but 169. When you expand all these terms and factorize, you will be getting the value for k as -3 and -47 divided by 3. So here we need to find the cosine angle between u and v, that is cos theta. Value what we know is inner product uv divided by norm u norm v. So uv, inner product uv is nothing but minus 1 into 2 multiplied by minus 3 into 4, we will be getting minus 10, and norm u is root of 1 square plus minus 3 the whole square, which gives you root 10, and for this we will be getting a root of 2 square plus 4 square, which is root 20. This can be written as 2 root 5. And now cos theta is inner product uv by norm u norm v, so minus 10 divided by here what I can do is I can write this minus 10 as minus 10 as root 2 into root 5, and what we know is root 5 into root 5 is nothing but 5, so these 5 and 2 will get cancelled with this minus 10, leaving us minus 1 divided by root 2 as our answer. For the second sum, we do have u and v. 3 into minus 1 is minus 3, 8 into 0 is 0. So when you take the inner product, third sum, when you take the inner product for these two guys, what you will be getting is the inner product itself is 0. So obviously we can conclude that the value for cos theta is 0. Okay, so next is the way to find cosine angle for the case of two polynomials p and q. So for the case of two polynomials also, we need to make use of the same concept, nothing will change. So we need to find inner product between p and q, that is minus 1 into 2 is minus 2, 5 into 4 is 20, 2 into minus 9 is minus 18. When you add, you will be getting 0 as your answer. So what we can tell, no need for us to calculate all these guys. So straight away you can write the value for cos theta as 0. Next is the concept of finding the cosine angle for two matrix A and B, and what we know is the inner product for A and B is 2 into 3, which is 6, 6 into 2, which is 12, 1 into 1 is 1, minus 3 into 0 is 0, so this gives us 19, and norm A is nothing but root of 2 square plus 4 square plus minus 1 square plus 3 square. So 2 square is 4, 4 square, sorry, I am telling it wrongly. We need to calculate for these two matrices. Upper root of 2 square is 4, 6 square is 36, 1 square is 1, and minus root 3 is 9. We will be getting root 50, which is nothing but 5 root 2. Similarly, when you calculate it for B, you are getting root 14, which we can write it as root 2 into root 17. And replace it back in the formula, that is here the formula is in product between two matrix A and B divided by norm A and norm B. Just do replace it, simplify, you will be getting your answer. For 10th sum, here they told that u and v are orthogonal to each other, and we need to find the value for this guy. So if u and v are orthogonal to each other, we know that the inner product between u and v is 0. So just you need to multiply 2 into 1, 1 into 7, 3 into k. 2 into 1 is 2, 1 into 7 is 7, 3 into k is 3k. When you multiply, you will be getting 0. So 3k equal to minus 9. This gives you the value for k. So next sum is we need to find the Cauchy-Squartz inequality. We need to verify Cauchy-Squartz inequality for these 4 problems. So let me do the first problem alone. Here the value for u is given as 3, 2 and v is 4, minus 1. Cauchy-Squartz inequality is nothing but modulus of inner product uv is less than or equal to norm u into norm v. So we need to find first inner product between u and v. Multiply these two. 4 into 3 is 12 plus 2 into minus 1 is minus 2. You will be getting 10. And this mod will convert your negative value into positive value. It is already positive, so we will be getting the same. Next, norm u. Norm u is equal to root of 3 square, which is 9, 2 square, which is 4. That gives you root 13. Norm v. Root of 4 square is 16, minus 1 the whole square is 1, gives you root 17. And norm u multiplied by norm v is, will be getting, when you make use of the calculator, you will be getting 14.87 as your answer. So what we are ending up with is 10 will obviously less than or equal to 14.86. Hence the Cauchy-Squartz inequality is verified. Okay. So the next sum is we need to find the basis for orthogonal complements of the subspace of Rn spanned by the vectors, all these vectors. So we are going to make use of the theorem. So we have already come across the theorem which states that the row basis, the null space of A and the row space for A transpose are orthogonal complements of each other. So we are going to make use of this property, this theorem, to find the solution for the last problem. So write the given vectors in 3 columns. You will be getting this W. Convert this to an upper triangular matrix. So you see, when you observe, you are getting 1 0 row which corresponds to the null space. So there do exist one basis, there do exist one vector in your null space. So we need to find, there are two non-zero rows in your row reduced column. So this corresponds to basis for row space are 2, and this corresponds to first row and second row. So that is what I have written here. And as there is one free variable, it corresponds to x3. So usually we'll be considering it as a variable t, and express x2 and x1 in terms of t. So here we are getting x1 as 16t, x2 as 19t, and x3 as t. And the basis for null space will be 16, 19, 1 in a column. So here usually t will write for the case of the solution, but for the case of basis we won't write t. We'll be considering the vector alone. So we are going to check whether this basis for row space and the basis for null space are orthogonal to each other. So take dot product for this 1, minus 1, 3 and 16, 9, 1, you will be getting 0. Similarly, for this guy to this guy, you will be getting 0. So with this, what we can conclude is that the basis for row space and the basis for null space are orthogonal complements for each other. Thank you.